Assalamu alaikum. Can you all hear me? Can you all hear me? Is my voice good? Okay, so and is the screen visible? Okay, so today we'll be doing questions regarding momentum, but before I get to these actual questions, I would like to recall some of the theory, and it will just be a quick review because the actual application of the theory would come when we doing questions. So that's where we discuss things in detail. Okay, so uh, from your O levels, most of you or all of you know the three laws of Newton that basically describe force. The first law of Newton was something that described the nature of a force, which told us that a force is something which causes a change in motion of an object or causes a change in the state of motion. So the first law was an object at rest would remain at rest, or an object at a constant velocity would remain at that velocity unless and until a resultant force acts on the object. And then the second law of Newton was something which quantitatively described this nature, which told us F equals mass times acceleration. So this now was giving us a numerical value of force for a given acceleration by a given mass. And then there was this third law, which described how the nature of force when it interacts with objects. So it was that basically when object A exerts a force at object B would also exert a force on object A, which would be of the same magnitude in the opposite direction and of the same type. So an example of this would be if I hit the wall. So at the same time, or not just a wall, let's say a person slaps another person. So when he slaps him, so he would feel something on his hand, and similarly the other person would feel something on his cheek. So both of them are feeling a force, and the person like his hand might turn red because he slapped someone. So obviously don't slap anyone, but a person who just slapped someone, his hand might turn red. And similarly, the person who got slapped might also have his cheek turn red. So both these things turn red because they were exerting equal and opposite forces on each other. So these were the three laws of Newton, which you all studied in your O levels. Now when we come to AS, so the laws remain the same, but we just now add momentum. So momentum is a quantity which we denote with P, and it's equal to mass times the velocity of an object. So the first law of Newton was an object at rest or a given state of motion remains in that state unless a resultant force acts on the object. And second law was, so that law remains the same. So basically this tells us that of an object, the momentum of an object remains the same unless there is a force on it. So that's how just we describe third law of Newton. That's how the dynamics change. And then this first law, the second law was F equals mass times acceleration. Now, since most of you are doing math, so I'll get into a bit detail regarding this. So basically, the idea was that this wasn't the final form of equation. The final form of equation was F equals basically when we describe the second law through momentum, we just say that force is now no longer mass times acceleration. Force is rather the rate of change of momentum, meaning change in momentum over change in time. So this is what force is to us now: change in momentum over change in time. We no longer say that force is equal to mass times acceleration. Rather, it's change in momentum over change in time. Why? Because there are two possibilities in this. One possibility is, now obviously we know that momentum equals mass times velocity. So obviously one possibility is the change in momentum was due to a change in mass. So we write like this. And another possibility for this is that the change in momentum was due to a change in velocity and the mass was constant. And we write this. And another possibility could be that the change in momentum was due to a change in mass and simultaneously a change in velocity as well. So basically, what I'm talking about right now is this was just a bit detailed. Uh, what I'm talking about right now is now we no longer define force being equal to mass times acceleration. We define force being equal to the rate of change of momentum, and the change of momentum could be change in mv over change in time. What we did in O levels was a very specific case where the mass was not changing, and most of the questions that you'll all be doing in your AS as well would have mass being constant, but there are cases where mass also changes, one of which we'll be doing. So if the mass of an object changes, there is a change in momentum, and then therefore there's a change in force as well. This kind of applies, for example, if you've seen rockets being launched. So when rockets launch and they're about to like leave the atmosphere, so what they do is they leave they eject some mass towards the earth, and that mass gives them a thrust upwards, and they move upwards. And similarly is the case with let's say fans as well. So if there's this fan, uh, or maybe just leave the example. Okay, so this is the case, and a very specific case of this would be where the mass was constant and there was a change in velocity. So this is what we always wrote as this thing was equal to acceleration. So there was this very specific case where the change in momentum was only due to the change in velocity. So that's when we tell it when we say that force was equal to mass times acceleration. So is this part clear to everyone, or should I like was something unclear, or did I make things a bit complicated here? Any questions, anyone? Okay, so I guess no question. Okay, so the next thing was regarding force, or to explain force in terms of momentum, is the third law. So initially, as per the first, uh, based on our understanding of O levels, we used to say that when object A exerts a force on object B exerts an equal force on object A, equal in magnitude, opposite in direction. This time, when we were talking about uh, when we're doing it in AS and we involve momentum, we say that the change in momentum uh, for object A, when two objects interact, the change in momentum for both the objects is the same and in the opposite direction. So let's say if I had a block, this pink block, and I have a blue block, they interact with each other, they hit each other, and they move in some direction. So based on the third law in on our O level understanding, we say that they exert equal and opposite forces on each other. But based on the understanding of AS physics and momentum, we say that the rate of change of momentum for both the objects. Now, rate of change of momentum was force. So instead of saying that they exert equal forces on each other, we now say that the rate of change of momentum of both these blocks is the same. So that's how we're now defining it. This is just one thing, how we would define these three laws, the three laws of Newton in terms of momentum. The next thing was law of conservation of momentum. So basically, there are ways to phrase this, but there is this law regarding momentum, like energy. Energy is always conserved. So then, similarly, there's this law that the linear momentum is always conserved. Or similarly, you could say that the momentum in a single direction in a direction is always conserved. They both mean the same thing. So linear momentum is always conserved, like it cannot change. So if there are two objects in a system, so the momentum of this system would always remain the same, whether they've like collided with each other, the two objects or however many objects may be in the system, or they've not collided with each other. So the momentum would always be the same. An example for this would be if I make this to be my system. And as a system means basically the region of an observation. So a system would be the region which is under observation. So inside the system, I had an object pink which was moving towards the right, and then there was an object which is blue which is moving towards the left. They would obviously collide with each other, and once they do collide with each other, they would like start moving in different directions. Let's say blue starts moving to the right and pink starts moving to the left, so they're moving in opposite directions. What we would know for sure is that the linear momentum which was before the collision, the linear momentum, initial momentum, is equal to the final momentum, because momentum in a closed system is always conserved. A system is what's the region under our observation, and when we say a closed system, what we mean is that there is no mass going out of the system, but like that's not something you're mm, not something very important. Okay, so linear momentum is always conserved. And obviously, when objects move, they have different kinetic energies, they have velocities, and they have kinetic energies. So there's a type of collision, or there are two type of collisions. One collision is elastic, and the other type of collision is inelastic. So these are the two type of collisions we would usually have in our physics. Elastic collisions are ideal collisions which usually don't happen in the universe, which don't happen in the real world. Inelastic collisions do happen everywhere around us. So the thing with elastic collisions is that the kinetic energy before the collision equals the kinetic energy after the collision. And similarly, when it comes to inelastic collisions, the kinetic energy, this I stands for initial and F stands for final. Kinetic energy before the collision and the kinetic energy after the collision are not equal to each other. So there is some loss of kinetic energy from these objects. So that's how we define elastic collisions and inelastic collisions. And then there was this idea regarding momentum, which was initial momentum equals final momentum. So this law stands for both of these equations, both of these collisions, whether it be elastic collision or whether it be inelastic collision, the momentum would always be conserved. And then depending whether the collision is elastic, kinetic energy would be the same or would be conserved, and if it's inelastic, kinetic energy would not be conserved. So if I rewrite this or I expand this equation, I get m1 v1 plus m2 v2 equals m1 v1 naught plus m2 v2 naught. Since the mass are same, there is the same, and this dash means basically after the collision. So I can simply write this equation like this, that the initial momentum, obviously we're considering that the object has two, uh, the system has two objects inside it. And then there's, if I now expand this equation, so I'll get 1 over 2 m1 v1 square plus 1 over 2 m2 v2 square equals 1 over 2 m1, and this is the final momentum, final velocity. So I write v1 dash whole square plus 1 over 2 m2 v2 dash whole square. So these are the two equations which I get, and when we uh, rearrange these equations, like do substitutions with both these equations, we get a results in the form of this. By the way, this is only the case, this pink is only the case with elastic collisions. So if it's an elastic collision, I can apply I'll get these two equations, and then I could apply, like substitute these equations, make v2 the subject of v1 the subject, and then I'll get a result of this equation. So this was just a summary of what momentum actually is. I hope this is clear to you. I didn't go into the proper details because only a short summary or a quick revision was intended. Okay, so now coming to the questions. So the first question is state the principle of conservation of, okay, by the way, is everything we've done previously clear to, is this all clear to everyone? If anyone has any questions regarding anything which you've done, feel free to ask. Okay, so I guess no questions. Then maybe it's clear to everyone. Okay, so state the principle of conservation of momentum. So the principle of conservation of momentum, as it is told, that for a system, the total momentum uh, remains constant, or as you could say that in a closed system, the total momentum remains the same, is unaffected by anything. So that's how we would define this. Part two, a ball X and a ball Y are traveling along the same straight line in the same direction, as shown in figure 4.1. They've given us the masses of both these balls and the velocities, their velocities as well. Now they're asking us to calculate the total initial momentum of the two balls. So we just need to find the total initial momentum of both these balls. So for that, we have their masses and we know the initial velocities. So that's what we add up. So m2 v2 initial momentum equals this, and I'll get m1 I know is 0.4, or not m1, let's say mx and vx. So that would be a better way to do this. Mx vx m by vy. So 0.4 times 0.65 plus 0.6 times 0.45. Can anyone tell me the answer? 0.53. Yes. 0.53 would be my initial momentum. And now they're asking me to find the velocity v. The velocity v is this velocity. So obviously, uh, what I do for this is I know that the initial momentum would be equal to the final momentum. And then I know that the initial momentum was equal to 0.53, so that would also be equal to the final momentum. And an equation for the final momentum would have been m1 v1 dash plus m2 v2 dash, or mx vx dash, or my vy dash. And then I have 0.4 times 0.41, because that's what they've given me, the description before the collision and after the collision, and plus m2, which is 0.6 times v is what I'm supposed to find, and this all is equal to 0.53. So can anyone tell me the answer? It would be something 0.53 minus 0.4 times 0.41 divided by 0.6. What would be the answer for this? So we would come out to be uh, 0.61. So this would be my velocity v, 0.61. So I just equated the momentum, that the linear initial momentum, the linear momentum before the collision equals the linear momentum after the collision. And now in the next part, they're asking me to find the total kinetic energies of the two balls. So since they're asking me to find the total kinetic energies of the two balls, so I could just simply find kinetic energies, and I have these values. So I just plug them in. The total initial kinetic energy. So I'll use the initial values, and which would be 1 over 2 m1 mx v square vx square. So times 0.4 times 0.65 whole square plus 1 over 2 times 0.6 and 0.45 whole square. So if I do this, I'll get an answer around 0.15 joules, or to be specific, it would be 0.145 joules. This would be my answer. So that's what I write. That's the initial kinetic energy. And then the next part is explain how you would check whether the collision is elastic. So how can I do that? So I just told that for elastic collisions, the kinetic energy before the collision is equals the kinetic energy after the collision. So to check whether the collision is elastic, we find the kinetic energy after the collision and see whether it's equal to the kinetic energy before the collision. If it's even a little bit less than it, means that the collision is not elastic. Next part is use Newton's third law to explain why during the collision the change in momentum of x is equal and opposite to the change in momentum of y. Okay, so I leave this part for now. When we do the next question, this part would become clear. There's some equations involved, or there's some actual reasoning why this is the case. This is basically Newton's third law, that the change in momentum of x is equal and opposite to the change in momentum of y. So why is that the case? Will become clear when we do the remaining parts. Okay, so if we move to the next question, they're asking us to define force. Now, what's a force? So force, obviously now in these questions, whenever it's uh, back in O levels, if there was force, you could have defined it as a push or pull or something which tends to accelerate object. But now, whenever now when we're in AS, if anything, if it's force or any of Newton's law, we define everything in terms of momentum. So we do know the formula that force is the rate of change of momentum. So force is something which causes a change in momentum in a given time. So that's what force is. And then the next part, state Newton's third law of motion. So now again, we need to state this third law. And the way we phrase it in terms of momentum is that the when two objects interact, when object A and object B interact with each other, uh, the rate of change of momentum of both objects is the same. Or just maybe just do it as you've done it in your O levels, that both exert equal and opposite forces on each other in the which are of the same type in the opposite direction of the same magnitude. Then the next part, which is like the important part, comes. Two spheres approach one another along a line joining their centers, as illustrated in figure 3.1. When they collide, the average force acting on sphere A is Fa, and the average force acting on sphere B is Fb. The forces act for time Ta on sphere A and time Tb on sphere B. Set the relationship between Fa and Fb and Ta and Tb. So, can someone tell me the relationship between Ta and Tb? Anyone? Okay, so uh, since Ta is the time during which sphere A was in contact with B, and TB is a time during which sphere B was in contact with A. So obviously they both would be in contact with each other for the same time. That's not possible that A was in contact with B for a greater time period than B was in contact with A. So obviously, since that's the contact time, it would be the same. So the answer for this would be TA equals TB. So that is how we would answer this. And the first part is state the relationship between FA and FB. So obviously from Newton's third law, we do know that FA equals negative FB. So that is something which we know. So use your answers and I to show that the change in momentum of sphere A is equal in magnitude and opposite in direction to the change in momentum of sphere B. That's what we need to show, and that's what they asked us in this part. So obviously, now that we know these two equations or we know these two relationships, I can move a bit further with this and write this as FA. Instead of FA, I could write change in momentum of A divided by TA equals change in momentum of B divided by TB. So obviously this was equal to FB and this was equal to FA. So now that I know that TA and TB are equal, I could cancel it out and I would be left with change in momentum of A being equal to the change in momentum of B. So this is how we show this mathematically. And obviously you could write this in words and give them the answer, which they're asking us that why is the change in momentum of sphere A equal to the change in momentum of sphere B. So you can just answer it like that. And as for the next part, for the spheres in B, the variation with time of the momentum of sphere A before, during, and after the collision with sphere B is shown in figure 3.2. The momentum of sphere B before the collision is also shown in figure 3.2. Now they're just asking me to show the variation with time of the momentum of sphere B during and after the collision with sphere A. So I have the initial momentum of both sphere A and sphere B, and what they're just asking me is to show the variation in the momentum of sphere B during and after the collision with sphere A. Okay, so until they collided, the collision took place at this point. So until both spheres collided, the momentum of sphere B would have been the same. And then I know that the change in momentum of sphere A equals the change in momentum of sphere B. This is something I know. Now I can find the change in momentum of sphere B. This is 6 and this is negative 4. So this change in momentum for sphere A, it goes from 6 to negative 4, which is a change in 10. Obviously, I could be making some mistake, but this is what I think it is. A change in sphere, 6 and negative 4. So the change in momentum of sphere A would be 10. And so I know that the change in momentum of sphere B would also be the same, and it's supposed to be 10. Okay, sorry. By the way, this wasn't 4. This was negative 3. This was negative 3. So the change in momentum was 9. Now I know that the change in momentum of sphere B would be equal to the change in momentum of sphere A. So this change should also be equal to 9. So this point is actually negative 4. And if I start with negative 4 and I do a change of 9, so I'll go get to a point around 5, this 5. So this 5 would be my point where my collision momentum would be after the collision. So I could write this is like this. I could continue it like this. The change in momentum of sphere B would have been 9. And just to join these, I can draw a line like this. This is how both of these would join. And by the way, just one thing which I think I missed. So I missed the sign. FA was equal to, the proper relationship would have been a negative sign because FA was equal to negative FB. So there would have been a negative sign over here, FB, and there would have been a negative sign here as well. So that's the remaining part in the graph, that The change in momentum of sphere A was -9, and the change in momentum of sphere B was +3. +3 because it went from -4 to +5. So I hope this part is clear to you. If anyone has any questions regarding this, just ask them. Otherwise, I'll proceed to the next part. Okay, so the next part, the variation with the extension x of the tension F in a spring is shown in figure 3.1. Use figure 3.1 to calculate the energy stored in the spring for an extension of 4 centimeter. Explain your working. So what we know is that okay, so if you've done the 3D of this extension and uh, stress and strain and these things, we know that if it's a force extension curve, the area under the curve gives us the work done or the energy stored. So this would basically give me, if I want to find the energy stored in the spring for an extension of 4 centimeters, I'll need to mark this region here. I'll just simply mark this whole region like this. And this whole area would just give me the energy stored in the spring. Because if it's a force extension curve, so the area of this would be equal to the work done, and that would be the energy stored by the spring. So this would be the energy stored. It's just an area of a triangle. So if I locate this point on this side, this comes out to be 160, 170, 180. So this probably comes out to be 180 Newton. So to find the area, I could just say 1/2 times 180 times 4 centimeters. And since it's centimeters and I need to convert it into meters, I divide it by 100 and then I'll get the answer. 1/2 multiplied by 180 times 4 divided by 100. So I'll get 3.6 joules. So this would be the energy stored by the spring. Now the next part, the spring in A. The spring in A is used to join together two frictionless trolleys A and B of mass m1 and m2 respectively as shown in figure 3.2. The trolleys rest on a horizontal surface and are held apart so that the spring is extended. So we've now extended both of these. And obviously, since when we extend the spring, the tendency of the spring would be to move to its original position. So there would be a pulling force that I would experience on my hand when I've extended these trolleys. Okay, so the trolleys are then released. So obviously there was this pulling force, and now the spring starts to pull them together. So when we release the trolleys, they start moving towards each other. Explain why. As the extension of the spring is reduced, the momentum of trolley A is equal in magnitude but opposite in direction to the magnitude of trolley B. So that's again, they're just asking me that why is the change in momentum of both of these the same? So obviously for that, we can tell that both these trolleys or the spring, right now the spring is involved, so the spring would be exerting equal forces and equal and opposite forces on trolley A and trolley B, because obviously both are different angles at different angles. So the spring would be pulling this object inside and pulling trolley B inside as well. So obviously if we see that the force on trolley A would be to the right and force on trolley B would be to the left, so obviously the forces are in opposite directions, and since it's a spring, so it's exerting equal forces. So the forces are equal and opposite. So force on trolley A equals force on trolley B. The next thing, just how we did it in the question before, the time for both of these would be equal to equal. So obviously we've done this part before. So you just now need to explain this in words and tell how we get to this derivation. That since they exert equal forces on each other, and the time of contact is the same, and force equals the rate of change of momentum. So the change in momentum of both these should be the same. So this kind of like this question is very important. If you've understood this, you can solve many questions like this. Okay, so at the instant when the extension of the spring is 0, trolley A has speed v1 and trolley B has speed v2. Write down an equation based on momentum to relate v1 and v2. At the instant when this extension of the spring is 0, trolley A has speed v1 and trolley B has speed v2. So how can we equate these? Anyone, any idea? Okay, so what we know from the previous part is that the rate of change of momentum of both these trolleys was the same. So we do know that the rate of change of momentum of trolley A was equal to the change in momentum of trolley B. Obviously, there was this minus sign as well. This is something which we knew. Now what we do is we just need to relate V1 and V2. And obviously, they've told me that the extension of the spring is 0, meaning that the spring has returned to its original position and the force has been applied, meaning that this force, that the pulling force that the spring was applying on both of them, it has done it and has now came back to its original position. So we do know this equation, and we just open this up. So ma v1 equals negative mb v2. So that's how we just equate both of them from this. And the next part, an equation to relate the initial kinetic and initial energy E stored in the spring to the final energies of the trolley. So the initial energy stored in the spring was E. So the initial energy stored in the spring was E, and then when the spring was when the trolleys were released, this spring started to pull both the trolleys on its right and its left. So obviously, if let's say that the spring was extended to 4 centimeters, it had some energy. It had some energy stored in it, which was 2.3 joules. So when I release this, the spring would start to pull both trolleys towards it and would tend to come back to its original position, its unextended position. So this energy which it had gained, it would start converting it into both these trolleys. And since it's applying the same force, now this point is also important. This trolley would be applying the same force on this spring would be applying the same force on both trolleys. It's not possible that trolley A would experience a greater force by the spring and trolley B would experience a lesser force or vice versa, even if their masses would be different. That could not happen. So the spring exerted equal forces on both these trolleys and it had some energy stored in it. So the way it would convert its energy would be in such a way that the total energy stored in the spring would be equal to the final energy stored in the trolleys. So it would be equal to the kinetic energy, the final kinetic energy of the trolleys. And this would be equal to 1 over 2 ma v1 square plus 1 over 2 mb v2 square. So this is how we just do it. And the next part, show that the kinetic energy ek of an object of mass m is related to its momentum by the expression. So for this, we just do a simple equation that we know that the kinetic energy for an object equals 1 over 2 mv square. Now, a very important thing is that I also know that P equals mv. So if I were to convert this into mv, I can just say that 1 over 2 m times m square v square. And similarly, I could say that this whole is equal to p square. So that's what they do. And I get equals p square over 2m. So that's simply how I get this result. And trolley A has a larger mass than trolley B. Use your answer in part 1 to deduce which trolley A or B has a larger kinetic energy at the instant when the extension of the spring is 0. Use your answer in part 1. By this, how can I deduce which would have a greater energy, greater kinetic energy? So obviously I have this equation MA V1 equals, now since I'm equating the magnitude, so I won't write this minus sign, MB V2. So if uh, trolley A has a larger mass than trolley B, so if trolley A's mass would be greater than trolley B's mass, obviously I know this from like simple math, the velocity of trolley A would have been lesser because its mass was greater. Because its mass was greater. And similarly, if its mass of trolley B was lesser, its velocity would have been greater. So obviously, kinetic energy is mainly dependent on 1 over 2 mv square. Mass is just single and v is being squared. So obviously, the dominating effect is of velocity. So any object which would have a greater velocity would have a greater kinetic energy. So from that, we can say that since mass A has a greater mass, it would have a lesser velocity compared to trolley B. And since trolley B has a greater velocity, its kinetic energy would be greater than trolley A's. So that's how we just simply solve this part. And then there's another question, which is state the principle of conservation of momentum. So obviously, we've done this previously as well, that the total momentum in a closed system is constant. So that's the principle of conservation of momentum. Very important term would be in a system. So that's important. The total momentum in a system remains the same. Okay, so the next part, the propulsion system of a toy car consists of a propeller attached to an electric motor, as illustrated in figure 3.1. The car is on a horizontal ground and is initially held at rest by its brakes. When the motor is switched on, it rotates the propeller so that the air is propelled horizontally to the left. The density of the air is 1.3 kg per meter cube. Assume that the air moves with this speed in a uniform cylinder of radius 0.045 meters. Also assume that the air to the right of the propeller is stationary. Show that in an interval of 2.0 seconds, the mass of air propelled to the left is zero point 0.3 kilograms. This part is simple maths. They've told me that this is the region where this is the area and the volume of the air. So what they've told me is that air comes out in the form of a uniform cylinder which has a radius of 0.45 with the speed of 1.8 meter per second. I could just simply say that the change in volume of the air, the volume of air that was being pushed was equal to hmm, volume over time. This is what I needed to find, right? So volume over time would be length times area divided by S. So L divided by S would become my speed, or a better uh, variable would be V. I just cite this as V. So I say V times A, velocity times area, and I get velocity multiplied by area. So I know the radius and it's 0.045. So I square this. So I square the area multiplied by pi and I'll get my velocity. So the velocity, and obviously I know V, uh, it's equal to 1.8. I multiply these and I get the change in volume. The volume of air that would be propelled or thrown by the propeller. So 1.8 times 0.045 whole square times pi, and I get 0.01145 meter cube per second. So this would be the volume of air that would be propelled per unit time. And I now know the density of air as well. So I could just simply, if I multiply this by the density, so I'll get the change in mass per second, or the mass of air which will be propelled in a second. So I just multiply this 0.01145 multiplied by 1.3, and I get 0.0149. So this is what I get, kg per second. This is the amount of, or the mass of air that would be propelled per second. And now I need to find the mass propelled in an interval of 2 seconds. So I just simply multiply this by 2. And obviously, when you multiply this by 2, I'll get a value 0.149 times 2. I'll get 2.9, not 2.98, 0.0298, which is approximately equal to 0.03, and what they've asked me in the question. So that's how we just do this. And then the next part, calculate the increase in momentum of the mass of air in part BI. Increase in momentum of the mass of air. So increase in momentum. So initially the mass or the air was stationary, and all of a sudden it got a velocity which was equal to 1.8 meter per second. So that's the velocity which it had. And obviously we know that the change in momentum is equal to mass, change in mass times velocity. It could have been like this, or it could have been other ways as well. Like change in momentum could either be equal to change in mass times velocity, or mass times change in velocity, depends on whatever is changing. So right now the velocity is not changing, the mass is changing because the mass is being propelled. So it's up to you however you do this, but the formula would be this. And I get the mass which was propelled to the left was 0.03 kilograms times the velocity, the change in velocity. So I multiply both of these, 0.03 times 1.8, and I get 0.054 Newton per second. So this is what I get, and this is the change increase in momentum of the mass of air. And then the force exerted on this mass of air by the propeller. So obviously, this change in momentum, this was my change in momentum, and this change in momentum was occurring. This change in momentum was occurring in a time interval of 2 seconds, which they've told me in the question. I just simply write force equals change in momentum over change in time. So I can write this as 0.054 divided by change in time, and the change in time was 2 seconds. So this would be 0.027, I think. Yeah, 0.027 newtons would be the force exerted on this mass of air by the propeller. And now they ask me that explain how Newton's third law applies to the movement of air by the propeller. Movement of air by the propeller. How the Newton's third law applies to this? So obviously, when the propeller exerts a force on mass A, or on this mass of air, and it propels it to the left, this mass of air exerts an equal force in the opposite direction, meaning the force exerted on this mass of air was towards the left. It exerts a force in the opposite direction, i.e., to the right, on the propeller. And since the propeller is attached to the electric motor car, the car starts moving to the right. So obviously, the answer to this would be the as the propeller exerts force on the mass of air to the left, the mass of air exerts an equal force in the opposite direction on the propeller, which is to the right. And then the next part, the total mass of car is 0.2 kilograms. The brakes of the car are released, and the car begins to move with an initial acceleration of 0.075 meter per second. Determine the initial friction force acting on the car. So the total mass of the car, we know it's 0.2 kilograms, and the brakes of the car are released, so there is no opposing force by the brakes, and the car begins to move within initial acceleration of 0.75 meter per second. So for this, we just first find out if we know the mass and we know the acceleration, can we find the resultant force on the car? The force resultant on the car would be equal to mass times acceleration, which would be equal to 0.2 times 0.075. So the answer for this would be 0.2 times 0.075. My answer would come out as 0.015 Newton. This would be the resultant force acting on the car. Now, when I talk about the car, there are two forces acting on the car. One is the force due to the propeller, and this force I've already calculated is equal to the force exerted on the mass of air by the propeller. It would be equal and opposite in direction, meaning equal to 0.027. So now I know this force being exerted by the propeller, it's equal to 0.027 Newton. So a force was exerted on the right, which was equal to 0.027 Newton. Now, there is a friction force acting on the car or maybe at the wheels in this direction. This is friction F. And the resultant of both these forces would be my resultant force F, F resultant, which I know, which I just found out to be equal to 0.015. And I also know if I make an equation for this, the equation would come out to be F resultant equals 0.027 minus F. So I'll get 0.015 equals 0.027 minus F, and F would be equal to 0.012. So 0.012 Newton would be the resistive force on the car. So is this part clear to everyone? Anyone who has any questions? Okay, so if not, then this is where we'll be ending the class for today. So I've kind of done all the type of questions that would enable you to like answer everything. So most of the questions, they would first ask you to state the principle of conservation of momentum, which you tell them is that the total momentum in a closed system is always the same. And then the other type of question could be why is the change in momentum of both the objects the same? So for that, we first start with the Newton's third law that when object A and object B interact, they exert equal and opposite forces on each other, which are given by this relationship, the first relationship. And then the time of contact is the same. So we say TA equals TB, and we use these two relationships to prove that the change in momentum should be equal and opposite for both the objects when they interact with each other. So these are kind of the gist of this whole thing. And other than this, they could ask you to find the initial kinetic energies or to determine whether the collision was elastic or inelastic and stuff like that. So I guess this is where we'll then end our class. So, okay, so videos questions and inshallah we'll meet tomorrow. So, Assalamu alaikum. Welcome.